Hello everyone, in this video we will be covering section 11.4, 11.5. 11.4 is the comparison test, and like it says, you need to compare two things to determine whether a series is convergent or not. The theorem says the following. If you have two sequences, so this is the one that you want to check whether it's convergent or not. This is the one you're going to use to compare. And for this one, usually you will use either the integral test or another test. Remember that the integral test gives you something called the p-test. And the p-test is you have to integrate something like this. This will be convergent if p is greater than 1, and divergent if it is less than 1. We'll be using that a lot in the examples. So there are two cases here. So case one, if this part is convergent and all the elements for this are less than or equals to the elements for the one you're comparing to, then the series you want is also convergent, which kind of makes sense, because if this is less than infinity, so you should think as convergent not being infinity. That's not quite true, but it will work for this case. So therefore, if this is less than this and this is less than infinity, well, therefore that means it's convergent. Excuse me. Now divergent is the opposite. If this is bigger than this, it is already infinity. So therefore, if this goes to infinity and this is bigger than that, it will also go to infinity. Okay? So to solve these problems is slightly different than the previous ones, but you're going to use the integral test, specifically the p-test, to check on that. So let's try this example. So here we have a(n) is equals to this. And this is what you want to check whether it's convergent or not. So we're going to use bn. Why did I choose that? Because I can already see that this is very similar to this, and I already know this is divergent. Why? So note, if you have this series from n equals to 1 to infinity, this is technically a p-series where p is equals to 1/2. Why? Because the square root of n is equals to n to the 1/2. So therefore, this series is divergent. So therefore, what we want to do is we want to prove case number 2. And if you can show that this is bigger than this one for all the values, then that will be correct. Okay. All right. So therefore, we start with this. Notice that if you have radical n, well, clearly is equals to radical n. That should be obvious. But what happens if you subtract 1 from here? Well, in that case, then clearly this will be less than or equals to that one. Also, note, this should be also obvious, but just in case, notice that 4 is less than 5, but 1/4 is greater more than 1/5. Okay, so therefore here, this implies that 1 over the square root of n minus 1 is greater or equal to 1/n. So remember that we say that this part was b/n, and this is a/n. So that shows that a/n is greater or equals to b/n. Since this is divergent, okay, because it's a p-series, then that means that the series, the original problem, n equals to 2 to infinity. So in this case, this doesn't matter if it is 1 or 2, so let's go with 2. That this and diverges by the comparison test. The comparison test. Okay, so the key is to show this part right here. Okay. But kind of ahead of time, you had to decide whether you want to make it convergent or divergent. So once you pick this, since you know this is divergent, you're trying to make it divergent. You would pick a convergent series, then your goal will be to make it convergent. All right, so just for notation purposes, I think I introduced this before, but just to be clear, I usually gonna use this for divergent and this for convergent, so that we don't have to write too much. All right, let's try another example. Again, this part right here, this is equals to an. Okay, so notice that you have n sine square n over n cubed plus 1, that this is less than or equal to n over n cubed plus 1. Why is that true? Well, the reason is that, remember, sine square is always less than or equals to 1. So that's why this is true. But also, notice that this is less than n over n cubed. Why? For the same reason from the previous problem. Okay, so this, remember, the nq is equals to nq, but if you add 1, this is greater, so that means that you do the reciprocal, this will be less than, in this case, less than or equals to nq. So this is why this is true. But notice that this is exactly the same thing as just 1 over n squared. You're reducing. And here, this is a p-series. Okay, so we're going to call this bn. And this is a p-series where p is equals to 2. So that implies that this is convergent. Okay, I'll probably show you that again in a little bit, but so for now this is convergent. Okay, so therefore this implies that an is less than or equals to bn for all n. So therefore, by the comparison test, okay, that means that this series n sine square n over n cubed plus 1 is convergent. And that's it. All right, now how do we know this is convergent? This is from section 11.3, I think. But just in case you forgot, let's say that we have this. So recall. So this is section 11.3. Let's say that you want to check whether this is convergent or not. So you use the integral test. Clearly this is positive and this is decreasing. Then the integral of 1 over x squared from 1 to infinity, this is equals to negative 1 over x. The integral from 1 to infinity, so it will be minus, it will be 0 minus 1, which is 1, so this is less than infinity, so that implies it is convergent. And this is actually true for any value for any exponent that is more than 1. If it is less than or equals to 1, it's actually divergent. And that's it. All right, so let's try one more example. So again, this will be an. That's what we're trying to check whether it's convergent or not. And we're going to start in a very similar way. N, notice that is obviously equals to n. But if you multiply n times ln, remember that ln, the graph for ln looks like this. It does goes to infinity, but since n is more than 2, so it will be this part. So you can see this is always a positive number and bigger. So therefore, if you multiply this by a number that is more than 1, which should be more than 1 eventually, clearly this has to be less than, greater than n, or equals to n. So therefore, this implies that 1 over n, ln n, is less than or equals to 1 over n, just like the previous two examples. And we're going to select this to be Bn, which is a p series where n is equals to 1. P is equals to 1, so therefore this will be divergent. Okay, so therefore, by the comparison test, since an is less than or equals, then bn, and since bn is divergent, then this implies that the series is also divergent. And that's it. All right, so now let's jump to the next test, which will be the alternating series test, which is actually a little bit easier than this one. We actually had to do another problem with the comparison test. All right, so again, here, notice that an is equals to n factorial over n to the n. Okay? So notice that this means n times n minus 1, n minus 2. So that's the definition of factorial, all the way to 2 times 1. And then on the bottom, you have just n by itself, n times. We have this n times. Now notice that for this part, okay, you have this. This is going to be less than or equals to 2 over n squared. Why is that true? Notice that if you divide this, like n over n is 1. So since this is less than n, all of these are going to be less than 1. So you could pick another number, but this will do the job. So you can safely say this is less than or equals than 2 over n. And you should recognize right away that this is a p series where p is equals to 2. Since this is more than 1, that implies that this is a convergent. So therefore, here an is less than or equals to bn. So we're going to select this to be bn. So by the comparison test, and that implies that this, which by the way, this is a series we're going to see a lot in the next or in the coming sections, that this is convergent. All right, now let's move to the alternating series test. This is probably one of the easiest tests to do. So here you're going to have a series that is alternating from negative to positive all the time. So for example, you expand this one, this is the same thing as minus 1 over n, and then this will be minus 1 over 2, or this actually can start in 1, minus 1 over 1, then plus 1 over 2, minus 1 over 3, and so forth. So that's what it means by alternating. Okay, and in order to be convergent, you have to check two things. First, that the function is decreasing, so is the function decreasing, so you need this to be decreasing, and two, that the limit as n goes to infinity of bn, where this part will be now bn. This has nothing to do with the comparison test. So all of this is an, and bn will be the part. So if the limit is 0, then if these two are satisfied, that means the series is convergent. If not, is divergent. So in our case, so let's check first part I. So bn here is equals to 1 over n. So how do we know that bn is decreasing? Well, there are two ways to do it, but the easiest way is to use calculus, change it to a continuous function. Notice that this is the equivalent. And if you find the derivative is this, which is always negative, which means it's decreasing. So therefore, the first part checks. And then the second one, notice that the limit as n goes to infinity of 1 over n clearly is equals to 0. So therefore, by the alternating series test, this is convergent. So as you can see, this is pretty straightforward. Usually the trickiest part is to check that it's decreasing, which all you have to do is take the derivative and make it negative. That's it. And check that it's negative. All right, let's try another example here. A n, remember the whole thing. And by the way, you could start in n or n minus 1. It doesn't really matter for the test. It will matter for other things, but not to check whether it's convergent or not. So here, clearly then, bn is just n over e to the n. So the first thing you have to check is this decreasing. So let's say f of x is equals to x over e to the x, okay? So notice that you can rewrite this as this, x e to the minus x. And if you take the derivative, use the product rule, this will be 1 times e to the minus x minus e to the minus x times x. So notice it will be e to the minus x times 1 minus x. And this will be negative if x is bigger than 1, which is the case because we're going to go from 1 to infinity. Why? Because remember, this is never 0. Okay, so recall that e to the minus x is never equals to 0. And the reason why is because the graph looks like this, so it never crosses this line. So therefore, that shows that it's equals to, that is decreasing. So therefore, this implies that n over e to the n is decreasing. There is other ways to show this, but by far this is the easiest way. And then number 2, you need to find that the limit as n goes to infinity of n over e to the n is 0. So notice the limit of this is actually infinity over infinity. So then by L'Hopital's rule, can use L'Hopital's rule, this will be the limit as n goes to infinity of 1 over e to the n, which is equals to 1 over infinity, which is 0. So therefore, this satisfies the two conditions, that is decreasing and that the limit is 0. So therefore, by the alternating series test, the series is convergent. The series which was 1 to infinity minus 1 to the n, and over e to the n converges. And that's it.